Last video we saw was about ionic bonding, and if you remember, ionic bonding is a bond formed between ions, which are charged particles. So we have atoms that have given or taken electrons to become charged, either positive or negative, and then the oppositely charged ions, the positive and the negative, will attract to form a bond. Covalent bonding is very different. There's no gain or loss of electrons here. There's no formation of ions. The big idea here with covalent bonds is that covalent bonds form when atoms share electrons. So not being selfish, not taking or giving electrons, they're sharing the electrons between two or more atoms. So covalent bond is a bond formed between two or more non-metals. This is no metals are involved. Remember, ionic bonds are between metals and non-metals. Covalent bonds are only using non-metals and metalloids sometimes, and they are sharing electrons, right? Remember when we were talking about ionic bonds, the representative particle, right, the smallest unit of measurement for it, or the smallest representative unit, was a formula unit. For a covalent bond, that representative particle is called a molecule. Okay, so formula unit is an ionic bond, molecule is for a covalent bond. Now what we see when we're talking about molecules is we actually work a lot with 7 diatomic molecules. And if you think about the word, or the prefix di, it means 2, right? So diatomic molecules are formed when 2 atoms of the same element share electrons. Okay, so it's a covalent bond. Electrons are being shared, and they're being shared between 2 atoms of the same element. Some examples, and these are really actually the only ones we see, H2, right? So covalent bond between 2 hydrogens, N2, O2, F2, Cl2, Br2, and I2. These 7, so hydrogen and the 6 that are here, are never found as individual atoms. They will either bond with different atoms or they will bond with themselves, okay? Now, if we look at the periodic table, these are kind of great to identify on the periodic table. Remember that there's 7 of them, okay? Hydrogen and the other 6 right here. Notice that these form a 7, all right? And if we're looking at the, I know I numbered these, right, just so you could count 1, 2, 3, 4, 5, 6, 7. But if we're looking at these on the periodic table, we see that it starts with nitrogen. I can't show you it right now, but it starts with nitrogen. Nitrogen is atomic number 7. So these form a 7 starting at atomic number 7 plus hydrogen. All right? So those are our diatomic molecules. Now, one specific kind of covalent bond that we also see is with acids. Now, these are molecular compounds, so they're covalently bonded, and they dissociate, which means they break apart into their ions, okay? It's a covalent bond, but they break apart into their ions when they're dissolved in water, okay? We always have H, so hydrogen, in front of our acids, all right? So when you see a formula for an acid, it'll always start with H. And remember that when we are writing our chemical formulas, we use a state symbol at the end. For acids, we will always see the state symbol AQ for aqueous because we've dissolved it in water. It's not an acid unless it's been dissolved in water. Some examples, hydrochloric acid, it starts with an H, it's HCl, and we would see AQ right there. Sulfuric acid, H2SO4, aqueous, right? Starts with H, state is aqueous. Now, when we're looking at covalent bonds, there's a couple things that we see with the actual bonds themselves. We have 3 types of covalent bonds that we see. We have a single bond, a double bond, and a triple bond. So right now we're thinking in terms of Lewis structures. What kind of bonds do we see? A single bond is one in which 1 pair of electrons is shared. Okay, so we're still sharing electrons, only 1 pair is shared. Our example here is methane. Now, I'm going to point you up here to this little note. A line represents one pair of shared electrons. That's 2 electrons. One pair is 2 electrons. So every time you see a line here, that's 2 electrons being shared. 1 electron is coming from the H, 1's coming from the C. 1 here is coming from the H, 1's coming from the C. All right, so that's what these lines mean. Shared electron is a covalent bond. All right, so 1 pair of electrons is being shared. CH4, we see there are 4 single bonds in CH4, in methane. We also see double bonds. This is one in which 2 pairs of electrons are shared. All right, so with oxygen, O2, remember this is one of our diatomic molecules, we have a double bond between the 2 O's. All right, so the double bond means that 2 pairs of electrons are being shared. How many electrons are being shared? 4 total electrons are being shared. In a triple bond, we have 3 pairs of electrons being shared. Nitrogen, N2 is our example. This is another diatomic molecule. This is an N triple bonded to another N. That's 3 bonds, that's a triple bond. How many electrons are being shared? 6 electrons are being shared, right? Because each line represents 2 electrons. Now, one important thing to note is that double and triple bonds are only typically formed with carbon and diatomics of O2 and N2 involved. So N2, O2, we'd see it with CO2, N2O, right? Now, we can look at the Lewis structures for actually writing the Lewis structures here for our covalent bonds. Now, what we're going to be doing is the same thing we did for ionic bonding Lewis structures, and that's using the octet rule. Remember that the atoms want to be like a noble gas. They want to have 8 valence electrons. So in this case, they're going to share electrons to satisfy the octet rule, to have a full valence. Obviously, with the exception of hydrogen. Hydrogen only wants 2 valence electrons, so that will not be going for the octet. So our steps here, the first thing that you want to do is you want to count the valence electrons in your compound. All right, so I'm going to point you down here. I've actually done that. My example here, NH3. I've counted my valence electrons. I have 1 N, okay? So there's 1 N. Every N has 5 valence electrons, all right? Nitrogen is right here, so it has 5 valence electrons. So that's a total of 5 electrons. I have 3 hydrogens. So here's 3 hydrogens. Each hydrogen has 1 electron, 1 valence electron. Hydrogen's right there. 1 valence electron. That's a total of 3 valence electrons. 5 plus 3 gives me a total of 8 valence electrons. All right? Now I need to make sure that in my Lewis structure I'm representing 8 valence electrons. So what we're going to do, we're going to draw the Lewis dot structure for each atom, and then we're going to draw arrows to complete the electron pairs. Okay? I'll show you what that looks like. Here, I have my Lewis structure for nitrogen, 5 valence electrons. Here I have my 3 hydrogens. They each have 1 valence electron. Okay, so there's my Lewis structures for each atom. Now I'm going to show arrows to complete electron pairs, so the bond forming. This hydrogen is not a pair, so it's going to come and bond with that electron. This hydrogen electron is not a pair, so it's going to bond there. This nitrogen is not a pair, so it's going to bond here. Now, what I wrote down here is very important. The central atom, so where these lone electrons are going, should either be carbon or the lone atom. Nitrogen here is the lone atom. There's only 1 nitrogen. So the electrons are going from hydrogen are going to be moving to that nitrogen. So what does this look like? We're going to draw what we have here. So we have 3 hydrogens, right? Hydrogen, hydrogen, hydrogen. Notice that I'm using bonds here, right? These arrows are now becoming lines. That represents 2 electrons for each bond. So I'm going to subtract 2 electrons for each bonding pair. From my 8, I'm going to subtract 6. I'm left with 2 electrons. So my free, non-bonded electrons remain as lone pairs. These 2 on nitrogen are going to remain as lone pairs. And those are my 2 electrons here. right? So I want to add up, make sure I have a total of 8 electrons shown. 2, 4, 6, 8. So this valence is satisfied. Over here, SO2, you'll notice that this one I've already drawn for you. If there's a double or a triple bond involved, like there is here, we will actually give you we'll actually draw this out for you. I'm blanking on the name. We'll draw this out for you. All you have to do is fill in the valence electrons where they go. So again, I'm going to count up my valence electrons. I have 1 S, all right? If I look at S here, it's an oxygen's group, so it has 6 valence electrons. I have 2 oxygens. They each have 6 valence electrons. That's 12. So I need to show a total of 18 valence electrons. Where am I going to show them? Well, all the atoms want to feel like they have a full valence. S right now has 2, 4, 6 around it. So it's probably going to have 2 more. Okay? Oxygen feels like it has 2, 4. It wants to feel like it has 8. Right? So I'm going to put 2 more pairs. Remember, we're adding these electrons in pairs. Same thing over here, oxygen. This one only feels like it has 2. It's going to want 6 more. So that's 3 pairs of electrons. Now they all feel like they have a full valence. Do we have 18 electrons shown? 2, 4, 6, 8, 10, 12, 14, 16, 18. 18 valence electrons are shown. All right, and what I wrote down here, if triple or double bonds are present, you will be given the structure. That's what the word is. You're going to add the electrons to that structure. All right? Now, the last thing that we're going to talk about is how to name covalent bonds. All right, so we talked about naming ionic bonds. Now we're looking at covalent bonds. Here are our rules. The first element, just like ionic bonds, that name stays the same. The first element, the name stays the same. The second element in the compound, the end is going to change to "ide," just like we saw in an ionic bond. All right, so it's going to be the stem plus "ide" at the end. All right, we're going to use prefixes. This is different from ionic bonds. Use prefixes to indicate the number of atoms. All right, this actually makes it a lot easier. The exception here is on the first element, if there's only one, right, our prefix would say use mono, but on the first element, if there's only one atom, we're not using mono. We'll just leave the mono off, okay? So these prefixes are right here in this chart. You'll also find them on the back of your periodic table right here, molecular prefixes, all right? They indicate how many atoms. So 1, prefix mono, 2, prefix di, 3, prefix tri, and so on all the way to 10, which is deca. If you're using oxygen, we're going to drop the A or the O at the end of the prefix before oxygen. For example, well, we'll look at that in a second. All right, I'll show you some examples. Rule 5, never reduce the formulas. Remember, for ionic compounds, if we had something like Mg2O2, we'd reduce that to just MgO. Here, the prefixes tell us exactly how many atoms, so we're not going to do any reducing here. There's 2 exceptions to our naming, and that's H2O, which you should all know is water, and NH3, which you may or may not know, is called ammonia. So these do not follow our naming rules. Now let's apply our rules. We have, for example, N2O. All right, I have 2 N's. I'm going to look at my prefix. The prefix is going to be di, okay? So di-nitrogen, okay? The name stays the same, but we have the prefix on it. So di-nitrogen, we have 1 oxygen. 1 is mono, okay? So this is monoxide. Now remember, we're going to drop the A or the O with oxygen from the prefix. This is not going to be monooxide. We've dropped that O to make it monoxide. It flows better. Our second example, SiS2. There's only 1 Si, but remember, for the first atom, we drop the mono. So this is not monosilicon, it is just silicon. S2 is sulfur. We're going to drop the ending and add ide, and there's 2 of them, so it's disulfide.